Hello and welcome back. In example 1, we're looking at does the series n equals 2 to infinity of ln n over n converge or diverge? Let's use the integral test to find out. So first we're going to write the function ln of x over x. This is the function that corresponds with the ln n over n, but just using a real valued continuous variable x. So this function is going to be continuous. Positive, and decreasing on the interval from x equals 3 to infinity. Now, the 3, where is the 3 coming from? Well, we're going to show that in the next step. The continuous and positive part, that one you can just state. Continuous is continuous because it's the quotient of two continuous functions, and at least on the interval from 3 to infinity, this is going to be continuous. The only place where maybe it's discontinuous is at x equals 0. Also, it's positive when you plug in positive numbers into when you plug in x numbers that are greater than or equal to 3 into the natural log, that's positive, and then x is positive, so these are positive numbers. Now the decreasing part is a little bit harder to see right off the bat. So what we're going to do is explain why it's decreasing when x is greater than or equal to 3. In this part, we're going to show where that 3 is coming from. Well, to show that a function is decreasing, you can look at its first derivative. If the first derivative is negative, the function is decreasing. So let's take the first derivative. I'm going to use a quotient rule. I'll sing my little quotient rule song. Low d high minus high d low over low squared. Little quotient rule song. And we've got 1 minus ln x over x squared. Now this is going to be negative for x greater than or equal to 3. And the reason for that is, well, first off, the bottom x squared is positive, so it's only when 1 minus ln x is negative that we're going to get a negative first derivative overall. So we're thinking when 1 minus ln x is less than 0, those are the x values where the first derivative is negative and therefore the function is decreasing. Let's solve this to figure out where this happens. Here we're going to apply the exponential to both sides. So you get x is greater than e. Remember, e is approximately 2.7. So 3 was just the next whole number after 2.7. That's where the 3 comes from. So now what we could do is we could look at the integral from 3 to infinity of ln x over x. Now that the conditions of the integral test are satisfied, and I should mention, when you're doing these integral test kind of problems, you'll want to state the conditions that need to be met for the integral test. So that's the conditions being that the function is continuous, positive, and decreasing. And that last one, that the function is decreasing, you'll want to show that by taking the derivative of the function and show that it's going to be negative, at least for the x values that are greater than or equal to the one that you find. This 3, by the way, in the integral test was the big N. This is like the big N from the integral test. Let's evaluate this integral, this improper integral. The first step is to replace the infinity with a t and let t approach infinity. Next, we're going to find an antiderivative of ln x over x, and here you can see that a substitution will work because we've got the ln x function whose derivative appears next to the dx. You can write the 1 over x dx right here. And as long as we're at it, we'll switch the limits of integration. I'm just going to do that directly in these limits. So when x is equal to 3, u is equal to ln 3. when x is equal to t, then u is equal to ln t. Then we have u du. So this turns into the limit as t approaches infinity of u squared over u from ln 3 to ln t, which turns into the limit as t approaches infinity of ln t squared over 2 minus ln 3 squared over 2. And that, when t goes to infinity, ln t goes to infinity. When you square it, that goes to infinity. This is minus a constant, so that's not doing anything. So basically this whole thing is going to infinity, which would say that this integral of ln x over x, at least from 3 to infinity, is diverging. So we can say, so by the integral test, since the integral from 3 to infinity of ln x over x dx diverges, the series then also diverges. Because the convergence and divergence of integrals and their corresponding series are tied together by the integral test. Now, one small thing to notice is that here we wrote the integral from 3 to infinity of our function diverges, but yet the series from n equals 2 to infinity of ln n over n also diverges as a result. So do we need to worry about the 2 and the 3 not matching? The answer is no. It doesn't really matter what x value or n value you start at. I mean, as long as the function is continuous and positive and decreasing on that interval, it doesn't really matter what starting point you have. And the reason for that is when you're trying to figure out if an integral converges or diverges, what matters is what happens in the limit. So it matters what happens in the limit as t approaches infinity, right? That's what really matters. It doesn't matter where we start at. This 3 could be a 5 or a 10 or anything like a 1, for example. It can't be 0 because you can't really plug in 0 into the function. But really the starting point doesn't matter. Those are just going to affect what you have, what constant you have. But that constant will not affect whether or not the integral converges or diverges. It's really what happens as the right endpoint of your interval, the t value, as that one runs to infinity, and what happens to the area under the curve then as you move to the right, as you add more and more area. So the convergence really depends on what happens as you go to infinity, not what happens when, or not where you start. So the 3 and the 2 can be different. These can be two different numbers, and that's okay. The convergence and divergence will still be tied together. Let's look at example 2. First thing we'll do is we'll say the function 1 over x squared plus 1. That's the function that corresponds with 1 over n squared plus 1. This function is continuous, positive, and decreasing for x greater than or equal to 1, it turns out, in this case. Let's check the decreasing. Where is it decreasing? Make a better C. Well, we can take the derivative, and once again, we can use a quotient rule. Low d high minus high d low over low squared. Brings a smile to my face every single time. Well, now this first derivative is always negative. This is negative And we're just going to write x greater than or equal to 1 because that's where n starts here. Let's just go ahead and match that. Again, it doesn't matter if they don't quite match. This could be like x greater than or equal to 10, and that's fine. But we can use this one if we can, and if we can't, like in the previous example, just go to the next integer where it works out. All right, so let's take the integral then of 1 over x squared plus 1, which as a first step, you replace the infinity with a t and take the limit as t approaches infinity. So we'll find our antiderivative. Remember, this one is inverse tangent x. So we've got inverse tan of t minus inverse tan of 1, which is the limit as t approaches infinity. Whoops. We're going to take the limit now. Getting a little carried away writing the limit notation. As t approaches infinity, inverse tangent is going to pi over 2. Remember, it has those horizontal asymptotes at pi over 2 and negative pi over 2. Going to the right, it approaches pi over 2. Then inverse tan of 1, that's pi over 4. So ultimately we get pi over 4. So we can say by the integral test, since the integral from 1 to infinity of 1 over x squared plus 1 dx converges, actually it converges to pi over 4 more specifically. Let's see, so we got this series also converges. Again, the integral test ties together the convergence and divergence of integrals and series. Now I do want to caution you that we don't know what the series converges to. We know what the integral converges to. It converges to pi over 4 based on our work to the left. But we don't know what the series converges to. Remember, they have different areas. Right? One of them is, when you're thinking about imagining what the series looks like, it's the sum of a bunch of rectangles that have width 1. But the integral is the area under a curve. So the areas are going to be a little bit different. So just because the integral converges to pi over 4 doesn't necessarily mean that the series is going to converge to pi over 4. So in fact, it's almost guaranteed not to converge to pi over 4. So we'll put a caution that the series does not converge to pi over 4. There. Now, one final note about this example is this. For the integral test, all we need to know is, does the integral converge or diverge? Now, we can do it directly by evaluating the integral. Right? And we take the limit as t approaches infinity and work out everything, and we eventually got pi over 4. But we didn't really need to know that we get pi over 4. All we need to know is, does this integral converge or diverge? Now in this case, we could have used a comparison test. Remember that we have a comparison test for integrals where we compare our function to some other function, and if the inequality works in the right direction, then we're able to get away with saying something about this integral without having to actually do the computation work. So let me write that over here in green. This is a big OR for this. You can use the comparison test for integrals. You can say something like, since 1 over x squared plus 1 is less than 1 over x squared, and the integral of 1 over x squared dx from 1 to infinity converges. This is like p equals 2, which is greater than 1. So does the integral from 1 to infinity of 1 over x squared plus 1. Because if 1 over x squared converges, then as an integral, then a smaller function will converge as an integral as well. So that's how you can use the comparison test to say that the integral from 1 to infinity of 1 over x squared plus 1 converges. And then from there you would finish it off by saying, so by the integral test the series also converges. Now, having said this, we're going to have in the next section a comparison test for series that's going to work in a very similar way to the comparison test for integrals. Thanks for watching, and see you next time. Oops, I forgot one thing. On the next page, we're reminded of the integral from 1 to infinity of 1 over x to the p, how this converges if p is greater than 1 and diverges if p is less than or equal to 1. This is something that we showed back when we talked about improper integrals. Well, it's not too surprising that the similar series 1 over n to the p is going to converge and diverge under the same conditions. And basically, you're going to use the integral test to help you figure this out. Now, the full formal proof is on the last page, but for now you can just think the same rules of p for 1 over x to the p, that integral, apply to the series 1 over n to the p. So the series 1 over n squared converges because there p is greater than 1. It's 2, so which is greater than 1. And the series 1 over the square root of n, that one diverges because there the p is a half, which is less than or equal to 1. So I wanted to mention that one last thing. Now, thank you for watching, and see you next time.